Okay, my slides here. Okay, good morning. Yes, I will talk today about demand-side flexibility in buildings, and I will talk a little bit about also a couple of case studies, what we have done it in the Finnish situation. So the outline of the talk, I will talk about some words about demand for the energy flexibility, and a couple of words also for the flexibility indicators and control strategies. And then finally, I will have three use cases of energy flexibility in buildings and also energy communities. So first of all, I think when we talk about smartness, we have a definition that is released in the EPPD SRI definition that what is the smartness of the buildings, and that that buildings are able to sense, interpret, communicate, and actively respond of the users change. So it means that demands for the building occupants is also included there. And for that, this SRI index, so smart readiness indicators, have been launched, and that measure the readiness of the building to adapt for the response of the users, readiness of the building to handle this maintenance and the fault diagnosis, and mainly that is the most important, this indicator is readiness to adapt for the smart grid and smart energy systems there. So these indicators at the moment is in the testing phase in Europe. At the moment, 7 countries are now testing that and looking for how well this is easy to adapt there. So how this indicator is measure readiness is not really measure actual how smart they are or how smart the algorithms are. It's measure more like how well buildings are equipped with different services and service levels there. So all these things is coming from the change of the energy systems in the market, and many countries in the near future, the energy production is based on the renewables. And when we have more solar energy and wind power, it's meaning that we have huge fluctuation in the market of the prices. And like in the Nordic countries, we have Nord Pool price, which indicate the price 24 hours ahead a day, or hourly price for the thing. And these markets are looking for what is the supply and what is the demand. And in the near future, we can estimate that this price fluctuation should be increased. We have even some cases in the situation like in Finnish that the energy price can be negative. So we have some days, some hours that energy company in principle paying that you consume electricity there. So this fluctuation definitely that will increase in the future, and that's the thing how we should make all the buildings more flexible for situation. In the spring, we will change the market so that we have the time step with the 15 minutes. At the moment it's 1 hour, but quite soon we are talking about 15 minutes time step for that. So what that means in practice, that here in this slide there is a dynamic energy price for electricity, and we can see that there's a quite huge difference of different days and different hours. And that make the motivation for the building owners to control their electricity use, when they use and how they use it. Also, in the near future, it could be estimated that also district heating price will becoming more dynamic. And on the right side, the panel is indicate dynamic energy price of one district heat company, how it look like. Because also there, its production cost change quite a lot depending about what kind of system they have to use in the production there. At the moment, we don't have this dynamic price in the market. We have a seasonal price for the district heating, but it could be estimated that in the near future also we will have dynamic energy price for the district heating and district cooling, because big part of the production is based on the renewables. So that gives quite a lot of possibilities to develop about new business models and new control strategy there, and optimize when and how to use either heating, district heating, or electricity in the buildings. So the methods of demand response could be like that, an idea we control when we use the power and energy, and we can make a peak cutting, we can fill values, or we can make a load shifting in principle. So idea is that the transfer the energy use for different time periods when energy price is cheaper. So motivation is coming from energy prices. Coming back, dynamic energy prices, hourly price, make a motivation for building owners to control the energy use. It's also quite obvious now that we talk more about power. So power is now coming as important as energy itself, because we have some cases and some countries situation that we have a lack of power. And the power price and tariffs are now changing so that the power is coming more and more important. Energy is one part of it, but also the power is becoming very important. Then, when we're looking for the flexibility factors, there is introduced, I think, maybe 40 or even 50 different factors for measure energy flexibility of buildings. And they could be categorized for three different classes here, like time, so temporal flexibility. When we are using the energy, it could be the one part of the indicator to measure. Other is that energy and power modulation, meaning that when we are using energy and how much. And then the last category is the cost. So how much we can able to save for building owner point of view when we have this energy flexibility implemented in the buildings. So even this sounds very simple, but in practice these indicators can create it quite complex thing, and if you are more interested about that, you can find a lot like an IEA report. There is introduce many of those flexibility factors. But maybe the most important is the monetary value. When we talk about the building owners, they're looking for how much they are able to save with this energy flexibility. So the cost is quite important motivator finally. So I have here a couple of use cases, and first one is here is a district heating building in the Finnish, and this case is analyzed for that, what we can do there. And the idea is here that like in Nordic countries, in Scandinavia, district heating is the one of the major energy source of the buildings. So all the cities, big cities, mainly we are using the district heating for heating the buildings. And it's also now coming more important to looking for what we can do there, how much we can make a flexibility of that. So we can looking for how we can reduce the peaks when the energy production is more expensive in the power plant. And on the right here, there is a synthetic price of one city in Finland. Is the price of the Espoo city, how it looked like, how the energy price in actually varied with the different hours. So we can do it that we can cut the peaks, we can using the building own thermal mass as a part of the flexibility, but also we can implement here short-term energy storage in the building. So we have small water tank in the building. So when we are looking for this pricing and using the control principle, one possible option is that we have rules there that we are earlier fixed what we do it, and looking for when the energy price is cheaper and when it's more expensive, we react that. And we can fix there some kind of threshold values which are constant value, or we can use, as in this case, this kind of trends. So if we're looking for price trend, if the price is increasing in the future, we can charge the building earlier. And during the expanding time, we cut the energy use. And when the price is coming more normal, then we are heating up the building. So this is base of the signal for the rising or falling price trends. Also, we can have model-based control strategies that make more complex and take into account many different factors, and that's making maybe more sophisticated method. But I put it here as an example that is quite logical to look what we do it when we have varied price, what we can able to do there. So when we have district heating buildings, we have two options to utilize thermal mass. We can either use centralized control like inlet water temperature for heating system, like commonly we have either water radiators or floor heating, radiant heating system. We can control that centrally, or other option that we have each water radiators, we have electronic thermostats that make possible to control the heating in different spaces more accurately. And if we have a space control principle, we prevent also the trend that some areas are overheating or overcooling, like what could happen with the centralized system. So big advantage to utilizing the thermal mass is that we have individual controllers in each space. So there is a market already available electronic thermostats that base of the cloud can be controlled. So they are IoT systems that base of the price can reduce or increase heating power in the space there. So there are some kind of small motor valves that are using. So it meaning that we are charging and discharging the thermal mass in the building based on the price. So that's the main principle of that. Then other option is that we have short-term energy storage in the building. So we have a small water tank that we are charging, and with this way we can cut the peaks. And like here in this case, we have a water tank that is integrated with district heating substation, so that we are charging that and then using this energy when the energy price is very expensive for domestic hot water, space heating or ventilation system based on the demand. One thing here is very important is to note that when we are integrated this kind of water tanks in the system, we have to guarantee that the return water temperature is not higher than 43 degrees. That is the fix in the like in the district heating system in the Nordic countries. That have to be guaranteed, and that's very important that this cannot destroy that, because then we are causing big problem for the power plants. So we have two ways to cut the peaks. So we have a building thermal mass, and then we have a short-term energy storage in the building. In this case, what I have a result is a 5 cubic meter tank that is still reasonable size to implement in the real building based on the space constraint. And here is the result. So these results are based on the calculation, so it's calculate how much we can cut the space heating peaks. And first of all, we have, when we change the temperatures, we vary the room temperature, but the baseline here is that if we have demand response space heating, we can able to cut around 6% of the space heating cut, but when we have using this energy storage, we can increase this flexibility up to 8%. And if we're now looking for what could happen for the power cutting at the same time for the tariff, we are able to cut the maximum power demand for the thing, and based of the energy tariff, that has big benefits for building owner, because we don't need so high peak power. Like in this case, we can reduce that 44%, so it's meaning for the building owner around 22% saving for the energy cost. So it's a combination about thermal mass, short-term energy storage for energy prices, but also when we cut the peak demand, we can get huge saving for the building owner side. So this example is make over 20% saving for that. Then if we're now looking for what that meaning for energy flexibility, we can calculate the effect how much we are charging and discharging of energy based on this strategy, and this meaning that we are a level of about from 5 up to over 15% of energy flexibility meaning. So it's meaning that we transfer the energy uses for a more cheaper time, and that how this indicator is working. So energy flexibility with the thermal mass is slightly higher for water tank in this case, but the power cutting is reduced quite a lot of flexibility. So it's meaning that that's very, very important for the using. So we can transfer about almost 20% of energy for that point. Okay, then I have other use case here is a little bit more complex building. So it's a hybrid heating system. So in this case, there is a ground source heat pump together with the district heating integrated there. So this building is how it looks like. It's about 40,000 square meter buildings, and it has district heating connections, but major part of energy is coming from ground source system, where we have 47 of boreholes, where average depth is about 320 meters. That is quite typical in Finnish side. So almost the whole area of the lot is fit for these wells there. So in this case, the heat power is about 800 kilowatts, and the district heating power demand is 1,680 kilowatt in this case. So they work in the parallel. Also, this ground source heat system is used in the summertime for the free cooling. So the major part of the cooling energy is coming from the ground. And also at that time, we are charging the ground for the next winter time for your use. So it's very beneficial to use ground for the cooling and heating together. Anyhow, in the Nordic conditions, the heating demand is much higher than cooling demand. So it's meaning that we are not able to charge in the summertime back in the same amount of energy that we are taking in the wintertime. Also, this meaning in the summertime that it makes sense to have room temperature reasonable cold, like 23 degrees, that we are able to utilizing this ground energy back, and we are charging the cooling energy in the ground. Okay, but this is the case that the idea here is to analyze how we can optimize of the use of the system, so that we have two energy systems there. We have ground source heat pump, and then we have district heating. And in the district heating, in this case, this is the base of the seasonal pricing energy, and the price signal is analyzed in the time horizon of 3 hours. So it's meaning that the system can be controlled in the 3 hours time period, not like an hourly, because it's not practical like a heat pumps on-off principle, so that they have certain time for the react there. So the idea here that when we are looking for this kind of system is normally it's like that we have a ground source heat pump as a base heating, and we are only using the district heating when the ground source heat pump energy is not enough. But in this case, when we optimize, this is coming from the base of the price signal. So cost optimal means here that if it's more economically to use district heating that heat pump, we are using more district heating. And here we can see the difference in this case that if we have normal base heating ground source, about 90% is coming from for heat pump, and then 10% is coming from the district heating. But when we are taking into account for the price, it makes sense to use more district heating for the hours when the electricity is very expensive. So in this case, it's about 80% of ground source heat pump and 20% of district heating. So we change quite a lot how we use for that. And we can see that from this duration curve, how it changes. On the left here, we see this base system that is normally used. That the blue line here is the heat pump. So we are using the heat pump as a base heating, and only the hours when we have high heat power, we have the yellow area, we are using the district heating. But when we are looking for this cost optimal control, we can use district heating during the whole winter time when the energy price is reasonable to use district heating. So this is the base of the electricity price and also the COP of heat pump. And then when we're looking for other duration curve, we can see that there's almost all the time for heating season, there's some hours it makes sense to use district heating instead of heat pump. So that meaning for this case that this energy cost saving is about 13% if we have this more modern control optimization system here. Okay, my last use case is a small energy community. This community means that we have here 5 educational buildings that are merged together with the low temperature heating network, where major part of the heating energy is coming from the waste heat of process there. So there's one building have a lot of waste heat that heat pump is using and distributing in the network 45% of the system. So it's meaning that we are able to utilize this low temperature system and then using also outdoor air as other energy source here. In the buildings, we have 2 separate heat exchangers there that we have in parallel, district heating, heat exchangers, and major part of energy we try to getting for this low temperature system there. So how it look like is like this here. So we have this low temperature heating network that is supplying 45 degrees water in the buildings, where also is other parallel heat exchanger for district heating. There is one exception, there's one new building part that is built for the low temperature heating system that is not needed to use for the space heating and ventilation district heating, because the whole system is designing for low temperature. But all the other buildings are old buildings, so they have high temperature demand there. So we need to have parallel district heating there. So we have heat pump, excess heat, and then we have outdoor air. So in this kind of system in the Finnish climate, it's challenging because we have time to time quite cold. And when the temperature is below minus 15 degrees, this heat pump is not used outdoor air as an energy source. Is only used this waste heat as the energy source because of the efficiency of the heat pump. So that meaning also for controllability point of view is a little bit more tricky in the climate. So here we can also see the prices, what are coming from electricity and district heating, and then we are looking for what are the hours. It's more profitable to use more district heating than heat pump. Now coming back, because we have varied energy prices there. And the whole thing is coming a little bit more complicated, because when we have this dual energy source heat pump, the COP of the heat pump reduced quite significantly when we go to cold weather, like minus 10 is COP is a 2.5, and if you have plus 20 is a 3.3 here. So if the temperature is below minus 15, the outdoor air is not using for heat pump because it's not make sense, because COP is reduced quite a lot. And in the Helsinki climate, we have time to time very cold. Our design temperature is minus 26 in Helsinki. So when we are looking for this similar duration curve here, that if we are using ground source heat pump as a base heating and then using district heating as a top of their energy ration for heat pump is around 57% and 43% for district heating. And when we are changing this cost optimal methods, so we are also utilize the dynamic price of electricity and district heating, we are consuming more or use more district heating here than heat pump. And now coming back, we have varied COP for that. So this analysis is done by the hourly base. And based of that, we are able to reach around 18% of energy saving for this control strategy. So coming back to conclusion, I think that it's quite obvious that buildings are needed to be more energy flexibility because energy production is based of the renewable energies. Like in Scandinavian point of view in the wintertime, wind energy is coming more and more important, and in the future is estimated that major part of our heating is based of the renewables. And that's meaning that we have to do it something measures also in building, and demand response is one option there. And based of this analysis, we can see that we can have range of 6 to 23% of saving for the cost when we are utilizing the dynamic energy price and also cutting the power demand. So big part of the saving is coming that we reduce the power what is needed in the building. Then other thing is quite commonly now that all the big buildings in the Nordic conditions are somehow merged together with two different systems like district heating and heat pumps. We have ground source heat pump, we have outdoor air water heat pump, we have exhaust air heat pump together with district heating, and it makes sense to optimize the uses of the system based of the energy price. And based of the analysis in this large building complex, we can reach easily over 10% cost saving when we are optimize what time we are using either heat pump or district heating and how much we are using that. And then when we are coming for the small energy communities where we have different energy sources and using waste heat there, the cost savings potential even larger. We can say that we are reaching easily around 20% saving for the small communities with optimize only the uses of the system based on the prices. So thank you. This is my talk. Time for the questions. Thank you.
Thank you, Risto, for your presentation.